Okay, so we've done about how the time of flight mass spectrometer works. Now we're going to do some calculations on it. So just to, this is our mass spectrometer tube here. We've got ionization occurs there, so we've got formed the positive ions in that chamber, and then they are accelerated. Sorry, they are accelerated here. And they all get the same amount of kinetic energy, which is kinetic energy is given by half mv squared. And finally, they're going to move down this tube with a certain speed, and so they're going to a constant speed. They're not being accelerated anymore, and they will be detected at the detector there'll be a time lag. Okay, so the faster ions will be detected first, the heavier, slower ions will be detected later. Okay, so here's a typical question. Okay, so they tell you this is the information they give you, right? Well, first of all, you want to find the time of flight for the 79 bromine ion. Okay, from that isotope of bromine. They tell you that all ions get a kinetic energy. We're given a kinetic energy of 3.65 times 10 to the minus 14 joules, so a pretty small amount of energy per ion. They tell you the length of the tube. The length of the tube is, or the distance is equal to 1.54 meters. Okay, and they also tell you the Avogadro constant. That's the number of atoms in a mole, which is usually given the symbol L, is 6.022 times 10 to the 23. Okay, so it's usually given to 4 significant figures in these calculations. Right, how are we going to do this then? Well, we know that kinetic energy is equal to half mass times velocity squared. How are we going to find out the mass? The mass of the 79 Br. Well, how are we going to find out? We know that 1 mole has a mass equal to 79 grams. Now, unfortunately, because this equation here, we're normally using grams as our mass, but it's not. You've got to use kilograms in this equation because you're using SI units, and so we've got to divide that by 1,000. So that's going to be 0.079 kilograms is 1 mole. And of course, we need to find out the mass of one of those. So of one ion is equal to 0.079 over the Avogadro number, 6.022 times 10 to the 23. Okay, so I'll do that on my calculator. Is equal to right 1.1 times 10 to the minus 25 kilograms. Okay, so we know the mass. Now, what else do we need? Do we know? We know that velocity is equal to distance over time. Where time is the time of flight there. So we know that v squared then is equal to d squared over t squared. Okay, so let's put some of that into some of those numbers into an equation then. Okay, so we know the kinetic energy, half mv squared. They tell us the kinetic energy, 3.65 times 10 to the minus 14 joules is equal to a half times 1.312 times 10 to the minus 25, multiplied by the distance squared. We know what the distance squared the distance is 1.5, so times 1.54 squared over the time squared. And the time is actually what we're trying to find out, isn't it? So let's do a bit of rearranging there. So we're going to get time squared is equal to a half times 1.312 times 10 to the minus 25 multiplied by 1.54 squared divided by this here, 3.65 times 10 to the minus 14. Let's do all of that. Right, so 0.5 times right, that's 4.26 times 10 to the minus 12. Right, that's t squared, so we want to work out what their time is. So t, square root of that, which is equal to 2.06 times 10 to the minus 6 seconds. Okay, so they're usually of the order of microseconds, 10 to the minus 6 seconds, very short time. That's the time of flight of the 79 bromine isotope. So that would be a typical question. It is quite, I think you're less likely to make a mistake if you put the numbers in sooner, but if you want to just, put everything in and rearrange everything, then you could do it like this. You could say, right, kinetic energy is equal to half mv squared. So kinetic energy is equal to a half mass times d squared over t squared. And we know that the mass of an ion, the mass of one ion, is equal to its molar mass, the atomic mass, mass of 1 mole, divided by 1,000, so it's in kilograms, and divided by L, the Avogadro constant. So let's put that in. So we get kinetic energy is equal to a half AR d squared over 1,000 L t squared. You get rid of your half there, can't you? So let's get rid of that and turn that into, that should be 1,000. Okay, that'll be 2,000 now. 2,000 times the Avogadro constant, squeeze it in there, L t squared, where t squared is your time of flight. So then you can rearrange. So like t squared is equal to AR d squared over 2,000 L times the kinetic energy. And if you just want to get t, square root that. Do that. That shouldn't be a minus, that's just a little bit of ink. Right, so that, that, if you wanted to rearrange it from scratch, that's what you'd get. Okay. We'll leave that there, but there will be one more video on that.